Hello, and welcome to the second tutorial session, which is intended for assignment 3. Just a reminder, this assignment is due on Sunday, which would be 9th of August, and hopefully, and remember that you can have multiple submissions of assignments. So even if you've already submitted the assignment, you could, and you want to kind of listen to this tutorial and go back to it, you're more than welcome to. But again, if you feel like you understand the subject well enough and you don't need this assistance, this tutorial is entirely optional. Okay. So let's start with the first question. This first question is, and many of these questions are multiple choice on which statistical test you would use. So the approach that I'm going to take is to just tell you a little bit about what we are asking about the question, and then talk a little bit about each of the choices. So on the first question, and let me start marking these questions, it might help. So I'm right now in question number 1. I say, which statistical technique would you use? We are an online shopping portal, so and we can tell if someone who comes to our website is a Mac user or a PC user. So that IP address, you can kind of say it's a Mac or a PC user. And we want to test the hypothesis that the ratio of people who buy out of those who log on, right, is higher for Mac users than PC users. So essentially, the data that you're going to see, the sample that you're going to see, is you're going to actually have a sample where you have a set of Mac users, and for each Mac user, your data point is that they either purchase or they don't. And similarly, you have a set of PC users. That size need not be the same. And the data point itself is either whether they purchase the product or not. And so for Mac users and PC users respectively, you're going to get a ratio or a percentage or a proportion. And what we're going to see is if one is higher than the other. Okay. Now that's the question. Let's take a look at the choices that we have. The first says it's a two-sample t-test, unpaired, unequal variances. So I'm just going to give you, for each of these, I'll just give you a quick example, and you can kind of see which example comes closest to the one that we just described. A typical example for a two-sample unpaired, unequal t-test, and the only thing that we need to keep in mind, the unequal variances is just affects the formula that you use. So you don't have to read too much into that. But for a typical two-sample unpaired t-test, an example that we've used in class is the heights of boys and girls in 10 standard. And so your sample there would be one set for boys and one set for girls, and each data point would reflect a certain height, and you're typically testing the hypothesis that the average height is the same or it's different. You're testing the null hypothesis that the average heights are the same. Obviously, when we say average heights, we're talking about the population parameter, not for just the samples. Okay. A typical example of a two-sample proportion z-test could be so again, keeping with the boys and girls, we could take something like the percentage of boys who pass a certain exam is equal to the percentage of girls who pass the same exam. So you might want to run a test saying that you take a sample. Let's say many boys and girls are given the same test, and then you take a sample set of boys and a sample set of girls, and for each boy you would ask the question, did he pass the exam or not? And so it's a binary thing, and that's the only data you have. And you would do the same with the girls, and you would see if the proportion is the same or not, meaning there would be some percentage of boys who passed. So let's say there were 10, 20, 30 boys and who took the exam, and let's say 12 of them out of 30, 12 of them passed the exam. So that's 12 out of 30. That's the proportion. And then similarly, you'll have some proportion for girls who pass the exam, and you're testing the hypothesis that these are equal. With the one sample proportion z-test, and so we've completed this option. Now we're talking about this option. The one sample proportion z-test, there is a single sample, meaning you are still interested in a proportion, but you might be saying something like, is the percentage of boys who pass a test like this equal to 80%? And so you have a number like 80%, and the only data set that you have is out of for a set of boys, how many of them passed or failed. So if you had a set of 30 boys and you had some number of them who passed the exam, you would see if that is statistically equal, if that can statistically be equal to 80%. The proportion need not be exactly 80% because that's the sample data set, but that's why we try to make a statement about the population parameter. Can you say something about the population parameter being equal to 80% based off of the sample? Okay. And finally, we come to single variable regression. Typically, in a single variable regression, what we mean by that is really a simple regression. So there's one input variable, and typically with that you have a continuous quantitative variable, that's the input variable, and you have a continuous quantitative variable, that's an output variable. You're looking to find a linear relationship between these two variables. So an example could be something like, let's see, what have we used in class? Something like, the speed that a car goes and the mileage associated with it. So you might have 10, 20, 30 data points on different speeds that cars traveled in, and the corresponding mileages that those cars gave. And you create a linear relationship between those two data points. So we've discussed the four options, and somewhere I think you would try to see which one comes closest to what we described in one. Okay, moving on to question 2. So let me circle that. We are an online shopping portal, and we can tell if someone who visits our website is a Mac user or a PC user. We want to test the hypothesis that among people who purchase something from our website, Mac users tend to spend more than PC users. So here the data is one where you have a set of data points for Mac users and a set of data points for PC users, and each data point reflects how much a person spent. So it's essentially like Mac user 1 spent 700 rupees on our website. Mac user 2 spent 300 rupees. And like that, you have a set for Mac users and you have a separate set for PC users. You want to test the hypothesis that among people who purchase something from our website, Mac users tend to spend more than PC users. So the first example is the two-sample unpaired t-test with unequal variances. This is the same option that we spoke about in the previous question. The typical example that corresponds to that, again, just to repeat what I said, is the heights, for instance, of boys and girls, where you have one data set separately for boys, one for girls, and each data point is individual heights. As I said, the unequal variances just characterizes the idea that you would have to use a different formula for getting the t distribution itself. Okay, so the second example is the second option for this question is the two-sample paired t-test. The key thing to distinguish between the paired and unpaired t-test is if each data point in data sample 1 has a corresponding match to a data point in data sample 2. So if, for instance, we gave the example of boys and girls' heights, if there was some connection between each boy to each girl in the two data sets. First of all, that would mean the two sample sizes need to be exactly equal, and second of all, it would mean that there needs to be some connection, and the connection could be something like each boy has a sister, and that sister is the girl in the other set, or that's the best I can think of right now. But other examples could facilitate very clear matches where each data point on dataset 1 has a match. So for instance, in our example, if the same user used a Mac and logged in, and the same user then used a PC and logged in, that could be some potential match, but that's not what's been described in the question specifically. So that's the two-sample paired t-test. The two-sample z-test, a big difference between the two-sample z-test and the two-sample unpaired t-test is whether you know the variance or not. So if you, for instance, know the variance, and you know, we also kind of talk about this idea where if you have a large enough data set, but like I've said in previous classes, just keep it simple. If you know the variance, use the z-test. If you don't know the population variance, use the t-test. So if you know the population variance, that would mean that someone tells you that, oh, I need you to do this comparison between the amount of money that Mac users and PC users spend on your website. But by the way, the variance of the Mac user spending is so much, either theoretically or through some other form of divine knowledge. You just know it. But here, by the way, here is the variance of the PC user. So if you know that, you could use the z-test, and that would be the right option. Finally, we come to the one-sample chi-square test. So we finished the two-sample z-test, and now we're talking about the one-sample chi-square test. With the one-sample chi-square test, you have a single data set, and you're really trying to make a statement about the population variance based on this data set sample. So you will take the sample variance and try and make a statement about the population variance. And since it's a one sample test, it's not like you're comparing two variances. You'll basically try and make a statement such as you'll try to make a statement about whether the population variance is equal to a particular number or not. So that's where you would use the one sample chi-square test. Okay. Going to the third question. So we are interested in understanding the difference between siblings. Specifically, we would like to study cases where there are non-twins but only two children in the family. We intend to test the hypothesis that the IQ of the elder sibling is equal to the younger sibling. Again, the examples for the two-sample unpaired t-test is one, again, of the boys and girls heights. You have two data sets. They need not be of equal sizes, but essentially you're trying to see if the height of the boys is equal, the average height of boys are equal to average height of girls. With the paired t-test, what you're doing is you're still trying to say if the average of data sample if the average of data set 1 of the population parameter, which is the average population, the population average of data set 1 is equal to the population average of data set 2. Exactly like in the case of the two sample unpaired t-test, but the one difference with the paired t-test is that there is a logical grouping between each data point in data set 1 and data set 2. So the question you would ask yourself here is that the case? We are trying to compare elder siblings, which is data set 1, and younger siblings, which is data set 2, but for each data point in data set 1, is there a corresponding data point in data set 2 which can be logically connected? Okay. We then have the third option, which is the ANOVA. So we've finished talking about the two sample unpaired t-test and the paired t-test. With the ANOVA, you typically use it at least in the context we are asking here, when you want to compare the population average of more than two data sets. So you have data set 1, 2, 3, 4, and 5, and you want to see if the population average of data set corresponding to data set 1 is equal to the population average corresponding to data set 2, is equal to the population average corresponding to data set 3, and data set 1, 2, 3, 4, and 5 can mean specific things. It can mean data set from city 1, city 2, city 3, city 4. It could mean from sibling 1, sibling 2, sibling 3, sibling 4. Or it could be anything. People from chemical engineering versus mechanical versus computer science versus civil. Whatever it is, manager A, manager B, manager C. But you have multiple headings, multiple data sets that you want to compare at the same time. And finally, you have this thing called the randomization test. That is not something that we've really covered in this class. So for this question and for subsequent questions, irrespective of whether you feel the randomization test is the correct answer or not, we don't want you to check that as the right answer. It's kept in there more as a dummy option, so you can just, for at least now, ignore it. Okay. So we've covered all 4 options in 3. Finally, we go to 4, where there are 6 sales managers who are deployed to 6 different cities. They are randomly rotated every 3 months, but it is ensured that each manager, so right now we are in question 4, let me just circle that, but it is ensured that each manager has only 1 stint in each city. After 6 such rotations, each manager has to be in each city once. Their sales numbers need to be compared to determine if the manager's performance is statistically different from each other. So the one important thing to talk about here is that there being 6 different cities is just coincidental. We're really interested in comparing the performance of manager 1 versus manager 2 versus manager 3 versus manager 4. Like that whole set of 6 managers, we're looking to see if there is any difference in their performances. And it could have been 6 cities, it could have been 4 cities, it could have been 10 cities. That just corresponds to the number of data points you'll have for each manager. But it being 6 also is just coincidental. And the fact that they're rotated every 3 months again is not really pertinent to this problem. So in your data set, you have 6 different data sets, 1 for each manager, and their sales figures in each city is a data point for each manager. So you have 6 data, coincidentally have 6 data points. We've talked about how regression is an approach where you have 1 or more input variables and you're trying, and all these input variables are typically continuous quantitative, and your output variable is also a continuous quantitative variable. Classification is these form of techniques where the output variable tends to be categorical. And here, if we need to think about what the output variable is, and here, for instance, it would be their sales numbers. And is the sales number something that's categorical? And in which case, you might be interested in looking at it as a classification problem. And finally, there's the ANOVA, where we spoke about how you have multiple data sets and you're comparing to see if the population mean corresponding to each data set is equal to each other or not. Okay. And last is the randomization test, which we are treating really as a dummy option. Okay. So we've discussed the 4 options. Let's take a look at the next question. Okay, question number 5. 2 different weight loss drugs are tried on participants who come in with a certain disease. Each participant is randomly assigned to one of the 2 drugs. The reduction in weight as a percentage is recorded for each participant. We would like to see if one drug is more effective than the other. Okay. Again, let's just straight off the bat ignore the randomization test. Okay. The critical thing to ask ourselves here is what is the data, and is the data whether they lost weight or not, in which case it would be a binary thing and it would kind of resemble that of a proportion, how many of them lost weight versus not. It sounds to me like what we are asking out here we're measuring the output essentially is the reduction in weight. So it's a number and it's a percentage, and in terms of understanding whether it's an unpaired t-test or a paired t-test, because so we just discussed the case of the proportion. To see whether it's an unpaired or paired t-test, one critical question to ask ourselves is there a logical pairing between the weight loss drug tried on a particular person, if weight loss drug A tried on a particular person and weight loss drug B tried on a particular person. I think the critical question is the same drug being tried on the same person? I mean, are the 2 different drugs, being tried on the same person? In which case, you might have a logical connection between each data point corresponding to weight loss drug A and each data point corresponding to weight loss drug B. You can say that the connection is the person, because it's tried on the same person. But if it's not, meaning if people are being randomly assigned to drug A and then some people are randomly assigned to drug B, you might not have equal size data sets, you might not have a logical connection for each data point, and at that point you'd be looking at the unpaired t-test. Okay, so now we are in question 6. Okay, we would like to test the hypothesis that the distance from a certain mall or a plaza in a particular city affects the price per square footage of houses within a 10-kilometer radius of the mall. Okay, so the thing you need to ask yourself is, what is your data here? And the quick answer to that is your data is really a whole set of houses, and you have 2 readings for each of these data points, which is the distance from the mall, so that will be in some number in kilometers or meters or something, and the price per square footage for that house, and like that you'll have many such houses, and that's your overall data set. We've spoken about the 2-sample unpaired t-test, where you have 2 data sets associated with the same output variable. The example we've always used is height, and data set 1 corresponds to, for instance, something like boys, and data set 2 corresponds to, for instance, girls. But essentially, for both boys and girls, or for any other, for younger sibling and older sibling, for whatever it is, you're still measuring the same thing. It's either IQ or height or something like that. With the single sample t-test, you are trying to say something about the population mean, but you have a single data set. You don't have 2 data sets. With the single data set of heights, say, you're trying to say, is the average population height equal to 130 or 140 centimeters. So it's like a very specific number that you're trying to see if the population height is equal to that. We've given you an example of a simple regression. We've spoken about how simple regression could be used. For instance, if you had a set of cars and you wanted to look at the relationship between speed traveled and mileage, where speed and mileage are continuous quantitative variables, and each data point would result in 2 values: one, the speed at which the car traveled, and its corresponding mileage, and like that you have many cars and you try to establish that relationship. Okay, and finally you have the chi-square test of independence. The chi-square test of independence is really used when you have 2 categorical variables. So something like gender versus pass rate, or it can have more classes also. It could be something like employment, type of employment, and likelihood of cardiovascular disease, where type of employment could have 3 or more classes, not necessarily just 2, and likelihood of cardiovascular we shouldn't say likelihood, again you want a discrete thing, but you could say risk level of cardiovascular problems, and the risk level could be low, medium, and high. So you have 2 completely separate categorical variables, and you are trying to again see if there is a relationship between these 2 categorical variables. So the question you should ask yourself in question 6 is whether the example that's been drawn out, the 2 variables of interest are categorical. Okay, so we finished with question 6 as well. We discussed each of these options. Finally, next question. So question 7. In question 7, we're interested in analyzing the 2011 by-elections in Tamil Nadu, which fielded 2 popular parties/coalitions. You're a cephalogist who's asked to see if there's any relationship between gender and the affiliation towards either of the 2 parties. However, you have no historical data and need to conduct a survey. You ask 100 randomly sampled voters and decide to do a statistical analysis to determine if there is any relationship. So let's take a look at the options that we have. The single sample proportion z-test is one where you're looking at a data sample of binary results, so yeses or nos, or the person bought or did not buy, the person is male or female. So there's some kind of a binary this thing, and you're trying to see if that proportion, right? Whenever you have a binary result, you can compute a proportion, the percentage of men, the percentage of people who bought. If that percentage is equal to some number, so you don't have two data sets, you have a single data set, and you're trying to see if that percentage is equal to some number. And when we say is equal to some number, we're talking about the percentage associated with the population. So obviously you take a data sample, but you're trying to say something about the population parameter, which is this proportion. You're trying to say, ask the question, is it statistically equal to some number that you have in mind. With the simple regression, again, we gave the example of car speeds in miles per gallon. Is that something that's similar to the problem at hand? The pair t-test would be one where you have two data sets that represent the same output variable, but data set 1 and data set 2 are for different for different inputs, such as the example we use for the pair t-test is let's say I'm thinking of an example like the wear on car tires. So if you are interested in testing the hypothesis that a particular track on which cars go, like let's say it's a racetrack, will have more wear and tear, more wear on the left tire rather than the right tire. So your data would be a set of left tires and a set of right tires, but there's some logical pairing between each left tire and right tire, and that logical pairing could be that they went on the same car. So you run 20 cars on this racetrack, and you measure the left tire wear and the right tire wear for each car. So you have 20 data points for the left side tire wear and 20 data points for the right side tire wear, but there's a logical pairing between each data point on data set 1, which is for the left tires, to data set 2, which is for the right tires. So is this problem something similar to that? And finally, you have the chi-square test of independence, where we said it's very useful if you have two variables, and these are completely separate variables, and each of these variables are categorical, which means it takes on some finite countable number of states. So something like yes, no, male, female, low risk, medium risk, high risk. And so both the variables should be of that type, and you would try and see if the frequency at which people or instances take up both these categories are independent of each other. So is there any relationship between let's say categorical variable A, which could be something like education level, which could have, let's say, 3 states, less than high school, more than high school, or let's just say it has 2 states, less than high school, more than high school. Does that variable have any relationship to low risk, medium risk, and high risk of cardiovascular disease? So 2 categorical variables, you're trying to see if there's any relationship. So we've covered question 7. We've discussed each of the options there. Let's go to question 8. In a simple linear regression, we use statistical inference to fine-tune the value of the coefficients in the linear model, ensure the unexplained error captured in the mean squared error, test the hypothesis that each coefficient in the linear model is statistically different from 0, and finally establish the intercept and slope values in a linear fit based on some objective for fitting a line through data. So really quickly, the idea behind using statistical inference in linear regression, in simple linear regression where there's a single input value, is to really see if what we're explaining with the input variable is actually contributing in any specific way towards better understanding the model. Excuse me. So um, we can follow some procedure with the data, but this data is ultimately a sample, and you can do some kind of optimization or whatever, and you can forcefully get some coefficient. So if you have a model which says y is equal to beta naught plus beta 1 x1, I can figure out some beta naught and beta 1 given a sample. But isn't it possible that x has no relationship to y? But because what would it mean if x had no relationship to y? That's the question. And the quick answer to that question is, if you take a look at so let me draw this, right? If x had no relationship to y, then technically a line that I draw between x and y would look a little like this, right? And so that's exactly what you're testing with the statistical inference, which is, can I reject the null hypothesis that this line should be like this, meaning it can be above or below all of these lines, all these three lines express that x has no relationship to y. So I don't really care about where this line kind of intersects y, but I really care about I really care to see if x has some relationship. So I'm really testing the hypothesis through statistical inference that this line is parallel to y. So that should kind of help you figure out which answer is correct. What would in this relationship, what kind of let's say you have mx plus c, or you can also think of it as beta naught plus beta 1 x1. What would the values of m and c have to be in order for this line to be parallel? Now we've covered question number 8. Let's go to question number 9. In a simple linear regression, we use optimization to determine if now you can actually read the options. I won't read all the 4 options, but let me just talk to you a little bit about, in a simple linear regression, why we use optimization, right? So the whole idea is, we speak about how you have a bunch of data points, right? And how in a simple linear regression you're trying to fit a line to go through these data points. And the core idea is that you can use optimization to figure out how this line should go through this data point, as long as you can create some objective. And a simple objective that we choose with simple linear ordinary least squares regression is to say, I want to minimize the distance of the cumulative distance of each data point to this line squared, right? Now the data points are fixed. That's the actual data, so you can't change them. The one thing you can do is you can change this line. You can either move this line up and down, or you can fix the line at some point and rotate it. Okay, so you can kind of move this line around, rotate this line around, such that the line that you finally decide minimizes the squared deviation, the sum of the squared deviation of each of the data point from the line. And that's where the optimization is. The optimization is one of minimizing this sum of squared deviation of data points from the line by changing the line, by changing where the line by moving the line up and down, and by rotating the line. So by doing that, we try to and once you're allowed to do either of them, you can create almost any line, right? Combination of rotating it and moving it up and down can create any line that you can imagine on this graph. And so we try to figure out that line which minimizes this. Question 10. A single sample t-test was conducted to test the hypothesis that mu naught is equal to 13. The data analysis resulted in the discovery of a sample mean of 14.5 and a p-value of 0.05. If we selected an alpha of 0.1, what would we do? The quick insight into this is that alpha is nothing but that value below which, if you get a p-value, you would then be willing to reject the null hypothesis. You're basically saying that alpha is that limit, essentially, where you say, if I get a p-value less than alpha, and the p-value here means something fairly so straightforward, which is it's the probability of seeing this data, and therefore this test statistic. It's the probability of seeing this value if the null hypothesis is true. Now, if the probability of seeing this data, if the null hypothesis is true, now if that probability is a really small number, and here then we are willing to reject the null hypothesis. And here the notion of really small is predetermined by a value called alpha. So you say, I don't want to do the test, so you say, if I get a p-value that's lower than alpha, then that's the limit beyond which I think the probability is too low, and so I'm going to reject the null hypothesis. I understand this kind of gives you enough direction, but just always remember, in the interest of learning, that you never accept a null hypothesis, or you never really accept an alternate hypothesis. Okay. We have finished question 10. Now finally question 11. A single sample t-test was conducted to test the hypothesis that mu0 is equal to 13. The data analysis resulted in the discovery of a sample mean of 14.5 and a p-value of 0.05. The 95% confidence interval around the mean would be. Just remember that when you build a confidence interval around a mean, you don't need a null hypothesis. Confidence intervals are synonymous in many ways. They're the other side of hypothesis test, but the critical difference is, in a single sample t-test, in any single sample test, there is a number you have in mind that you're hypothesizing, and then you take the data, you look at the data, and you try to test the hypothesis that the population parameter could be equal to this number. With a confidence interval, you have no such number in mind. Okay, the only thing that you have is the data, and the only thing that you can calculate is the sample mean of the data. Now, based off of the sample mean of the data and the data itself, you construct a confidence bounds. So essentially, the important thing to realize is that the confidence bounds have nothing to do with the hypothesized number. It has to do with the sample mean. It has nothing to do with what you're hypothesizing mu0 to be equal to. Now it winds up that because the p-value is exactly equal to 0.05, and that the 95% confidence bound is what we are interested in, that I think the important thing to realize is that you'll have a bound that's around 14.5, and because confidence bounds are the flip side of hypothesis tests, I mean, mathematically they're just an algebraic rearrangement. Your bounds would essentially be centered around 14.5 and would come one side down to 13 and the other side upwards symmetrically. Okay. Question number 12. We run a statistical test to see if the user satisfaction of two different cell phone UIs, user interfaces, are equal. We fail to reject the null hypothesis that they are equal. We want to increase the probability of finding any difference if there is one. In principle, we want to. So we've said that we originally failed to reject the null hypothesis, right? And we want to increase the probability of finding any difference if there is one. Now, that just readily means that you need to look at what the concept of type 1 and type 2 errors are. Type 1 error is the probability of incorrectly rejecting the null hypothesis when you should not have rejected the null hypothesis. Here the null hypothesis would be that they are equal. So if I incorrectly reject the null hypothesis, if I incorrectly go and say they are not equal when they are actually equal, then that's the mistake I'm doing. Okay, so would reducing that or increasing that achieve the goal that I want, which is that we want to increase the probability of finding any difference if there is one. Right? Type 1 error has to do with if there is no difference, saying that there is a difference, increasing or decreasing that. Type 2 error has to do with when there is a difference, failing to recognize that there is a difference, because the null hypothesis is that they are equal. So in the situation where the null hypothesis is not true is where type 2 error comes. When they are truly not equal, in the real world they are not equal, but from a statistical test I fail to tell you that they are not equal. I'm not able to tell you that they are not equal. So is that what we want to do better? And just remember that type 2 error is not a good thing, because it represents my inability to not tell you there is a difference when there is. So that's not something we want to have a high value. And just remember that power is nothing but 1 minus type 2 error. So power is a good thing. More power, better. Less type 2 error, better. Okay. I hope this helps you answer some of the questions in assignment 3. Just a reminder that the assignment itself is due on Sunday. And today, Friday, is the 7th. So 8th, 9th, Sunday the 9th of August, end of day is the deadline. And look forward to your submissions. Thank you.